In case R, we're looking at an application of the binomial distribution to be approximated by a normal distribution. In our case, we need to check to make sure that it's a valid approximation, and this won't take much work because of the way this works. Our value parameter p is given to us at 0.0007, and our n is a quarter million, so that when we calculate the two things that have to both be above 5, we need to make sure that n times p is greater than 5 and or equal to 5, and also that n times 1 minus p is greater than or equal to 5. Our n times p is equal to 175, and that's plenty big, and then this is going to be huge in comparison. So we're going to have a good approximation here using the binomial distribution, and because we have a mean near, whoops, I didn't draw a very good bell-shaped curve, because we have a bell-shaped curve with a mean of 175, and we're asking for the probability that no more than 200, so no more than 200 are problematic. So the answer is going to be pretty big given the fact that we're quite a ways away from the mean. Here it's useful to remember what the mean and standard deviation of the normal approximating binomial that we're going to use. The mean is equal to n times p, which we just calculated to be 175, and the standard deviation is equal to the square root of n times p times 1 minus p. And when I did this, I got a standard deviation of 13.22413. So with that, I'm ready to begin applying the expression and the approximation, and we're told that x is less than or equal to this value of 200 would be equal to phi of 200 plus 0.5. So we want to go at 200.5 or less. So that'll give us 200.5 or less. So we want that portion of the curve, and it'll be a fairly large one. And our mean is 175, and our standard deviation is equal to 13.22413. So I did this and I got a z, everything inside the parentheses. I got a z of about 1.93. And I say about 1.93 because I wasn't including very many digits, since this is just a normal approximating a binomial distribution. We don't want to get crazy with the digits. Now that I have our z, we need to find the phi of 1.93. We can do that using the tables. Do we have 1.93? Not quite. I need the bottom half. So looking for 1.93, I found it. 1.93, and phi is 0.9732. Let's check. Do we want that number or do we want one minus that? So phi of z, on zooming, was found to be equal to 0.9732, which we just got from the table, for phi of 1.93. Do we want that number, or do we want 1 minus that? Again, looking at our little sketch that we drew here, we want that number. So, in fact, our answer for case R is equal to 0.9732. And since this is just an approximation, I would probably just say 97.3%. And that's probably a better way to say this.